So we are very much seeing this as a real challenge that customers are facing, as a recent Capgemini report showed, in which 9 of 10 executives have reported facing ethical issues in the implementation of AI. And these executives cited reasons including the pressure to urgently implement AI, the failure to consider ethics when constructing AI systems, and a lack of resources dedicated to ethical AI systems. Artificial intelligence systems have a growing impact on people's lives on an everyday level. Thus, it is fundamental to understand models, protect people, and control AI systems. While machine learning services are constantly developing, Microsoft emphasizes the ethical principles that put people first, meaning that employees are working to ensure that AI develops in such a way that can be benefited in society while warranting people's trust. Before I go into the middle of this, let me introduce you very quickly. So I'm Eve Pardi, or Eva Pardi, a Microsoft AI MVP, and a software developer and data scientist at Leardal. Leardal is a company which actually has an office in Bangalore as well that aims to help doctors and nurses to save more lives all around the world. They provide online and classroom trainings as well, and different tools that helps them practice saving lives. And as you might know about me, I'm also trying to use AI to save more lives or improve the quality of life of people, and by using different intelligence applications, namely artificial intelligence. You're welcome to reach out to me an email, LinkedIn. You can find me on Twitter or Facebook as well if you want to learn more or get into this saving more lives with AI movement and so on. So the object of this session is to bring explainability into often confusing and complex AI systems, since these can sometimes behave strange for various not fully understood reasons, such as, for example, you might have heard about this issue at one of the banks that at some point started to give away some credit to people. And I don't know who was that who noticed that it most of the time gave money more often to men than to women. And it was simply because the AI system that was used for making the decision whether the person could get a credit or not, that was trained on a data set which included more data about men than about women. And so it is better to make sure that the AI system is trained on both sides as well. Otherwise, it would be maybe discriminative or something else that we don't want. So the tools discussed today can help developers to debug and fully understand their models. Furthermore, these aim to increase the understanding of intelligent systems for end users, thus building trust and power, which can assist users to make better decisions and accept and trust AI solutions. AI systems can behave unexpectedly for a variety of reasons. So fairness and interpretability tools help you to understand the behavior of your systems so that you can better tailor them to your needs. AI systems rely on data. These software tools can help you protect that data by preserving privacy and ensuring confidentiality. Responsible AI needs governance and control through the development cycle. Azure Machine Learning enables an audit trail for better traceability, lineage, and control to meet regulatory requirements. From the tools that can be used to help developers fully understand their models, in this session, I'd like to focus on interpretability. Interpretability assists data scientists to explain, debug, and validate their models, thus helping to build trust towards the model. InterpretML is an open source Microsoft package that incorporates ultra-modern machine learning interpretability techniques and can be viewed as a valid source for explaining black box systems or glass box models. The Azure ML Interpret package supports developers using dataset formats such as NumPy arrays, Pandas data frames, and so on, and furthermore leverages libraries like Lime or Plotly and offers new interpretability algorithms like Explainable Boosting Machine or EBM. So the interpretability package can be used for many data scientists, especially for startups and companies as an essential tool for model debugging, for example, to understand why that model made that specific mistake. Or if you have to detect fairness issues, whether your model discriminates. You can use it when you have to use a tool for human and AI cooperation, so understand and trust the model's decisions. And it is useful for regulatory compliance, whether your model satisfy legal requirements as well. And it is really useful when you have to build high-risk applications for example, healthcare, finance, judicial, and to understand the model's decisions that helps building trust among stakeholders and executives as well. So though tabular data is standard among machine learning scenarios, natural language processing has been growing in popularity with applications in topic classification, sentiment analysis, and entailment in wide variety of business scenarios. Okay, so for those who haven't used NLP before, I'm just mentioning here, it can be used for example, to tell what a book is about, or whether the comment on your Twitter post is positive or negative, and to understand and read the text from a document. That's really useful tools. So interpret text is an innovative interpretability technique for natural language processing models. And it has been developed by the community, and it has been announced at Microsoft Build in this year. It currently only supports topic classification, but it is planned that the repo would include other NLP scenarios as well. And here I have to mention that please, if there is a scenario that you want to see supported and it is not supported yet, feel free to let me know and we try to get it done for you. So this open source tool allows developers and data scientists to explain their models globally, so for each label, or locally for each document. So to build a visualization dashboard is also possible with these tools. And these dashboards provide insight into the data. You can also perform comparative analysis on the experiments while running them on different state-of-the-art explainers. Interpret text comes with explainers that support BERT or bidirectional encoder representations from transformers and residual neural networks as well as standard scikit-learn models. And with this open source toolkit, users will be able to take advantage of the state-of-the-art interpretability techniques with a common API across integrated libraries, as well as its own visualization dashboard for understanding which key phrases and words were important to your text classifications. And before looking into the different explainers, let me take a step back, because there are two broad classes of NLP approaches, the classical machine learning and the deep learning techniques. So in classical techniques, the first step is preprocessing, which involves steps such as tokenizations, normalization, noise removal. Then that processed data is fed into the model, which can be linear regression, like GBM, or random forest, of course. And the output depends on the scenario you are modeling for. So for some of these approaches, the internal functionality is very well understood, and as a result, the user is confident in the explanations provided. However, these methods, although widely adopted and easy to use, are limited in their accuracies on real-world datasets. But recent advancements in NLP owe a lot to developments in deep neural networks such as BERT. So these models have very high accuracies on NLP tasks. However, they are black box models and their decisions are quite difficult to understand. The research community has created a suite of state-of-the-art interpretable models, ranging from post-hoc analysis to plugins during training. Though promising, these methods are hard to implement in practice and not as accessible to data scientists. Therefore, to make these recent research developments more accessible for data scientists, in this toolkit, Microsoft has released OSS implementations of free explainers. They have implemented one classical and two state-of-the-art explainers that provide local explanations on the text document. For text classification scenarios to cover both NLP approaches, the classical text explainer, which is a standard set of glassbox models, the unified information explainer, which is a post hoc method and model agnostic, and the introspective rational explainer, which is a plugin method and also model agnostic. Now, let me talk a bit more about these explainers to give you an understanding of how they work. So, the classical text explainer is an interpretability technique used on classical machine learning models and covers the whole pipeline, including text preprocessing, encoding, training, and hyperparameter tuning, all behind the scenes. You can supply your dataset without any external procedures. And for preprocessing, it uses a bag of words encoder and logistic regression for training as a default configuration, which actually can be changed with the use of a configuration file. So as an input model, classical text explainer supports two model families right now, the scikit-learn linear models and the tree-based models. And additionally, any models with similar layout and suitability for sparse representation can be used soon. The API enables developers to extend or move around the different modules, such as the preprocessor, the tokenizer, or the model, and the explainer still can pull in and use the tools implemented in the package. And the explainer returns the importance of the word, how big effect the word has on the decision the model makes. We're going to see how this works in the demo. The Unified Information Explainer is a state-of-the-art NLP interpretability model. And this explainer is a post-hoc method, meaning it needs a previously trained or fine-tuned deep neural network model. Its support for explaining BERT is implemented and will be extended to other deep neural networks such as RNN, CNN, and LSTMs also in the future work. This method uses a mutual information-based approach, and it provides the importance of words as it goes through all the layers of the neural network. Since each layer is explained, the explanations about the transformer, pooler, and layers are unified and intelligible. And text preprocessing is handled by the explainer. The sentences are tokenized by this BERT tokenizer. And you can find more information in the paper that is written here. I can share this slide so you can have these links for yourself as well. The key task here is to associate underlying representations of the word with interpretable units in the hidden states of the layers. So we want to quantify how much information of an input word is included in each layer. So
Ma'am, you're on mute. Hello, ma'am. You're on mute.
Hi, can you hear me now?
Hello. Yes, ma'am.
Okay, where did you lose me? I don't know what
The
happened.
previous slide, ma'am.
Okay, sorry. I don't know how did I get muted. All right. So, okay, should I just start from the beginning of this one?
Yes, ma'am. That would be good.
Okay, sorry about that, guys. I don't know what happened. So, the Unified Information Explainer, this is a state-of-the-art NLP interpretability model. And this explainer is a post hoc method, meaning it needs a previously trained or fine-tuned deep neural network model. Support for explaining BERT models is implemented already and will be extended to other deep neural networks, such as the RNN, CNN, and LSTMs as well in the future work. And this method uses a mutual information-based approach, and it provides the importance of words as it goes through all the layers of the neural network. And since each layer is explained, the explanations about the transformer, the pooler, and the layers are unified and intelligible. Text preprocessing is handled by the explainer. Sentences are tokenized by the BERT tokenizer. And you can find more information in the paper here and the link there. And I'm going to share these slides and you can have these links as well for yourself. The key task here is to associate underlying representations of the word with interpretable units in the hidden states of the layers. We want to quantify how much information of an input word is included in each layer. So a very important word will have a lot of information encoded. So there are two forces at work here. As the word embedding is going through the layers of the DNN, it is perturbed by trying to add as much noise as possible. What we want to see is how much the output changes as the noise is added. So if a lot of noise affects the output, then it is an important word for that layer. If it doesn't affect the word, then it is not important. And on the other hand, the loss function tries to minimize the difference between the perturbed hidden state and the original hidden state, since we don't want to end up explaining a different model by perturbing it too much. These two functions work hand in hand to help us better understand how the words are being propagated through the layers of the neural network. And there is the repo here that has a sample notebook in there illustrating how to explain the importances of the words through the different layers of the neural network. And it uses the multi-label text classification scenario as an illustration. And we are going to take a look at it together as well so you know how to get started with it. The introspective rational explainer is the third state-of-the-art explainer. More details about this method are in the paper, but let me give you a brief introduction. This method introduces a plugin into the training process and makes the black box model more interpretable. This plugin is called the introspective generator. This introspective generator splits the text into rationals and anti-rationals. The rationals are a subset of the words that, according to the introspective generator, are important. Right? And on the other hand, the anti-rationals are not important according to the introspective generator. So this generator simultaneously trains the model on both the rationals and anti-rationals, and it tries to maximize the accuracy of the model when only using the rationals, and on the contrary, minimizes accuracy when using anti-rationals. Since the model only sees the rationals at training time to make a prediction, strong guarantees are provided about which phrases matter to the prediction. Generally, no other method provides such strong guarantees like this one. And the API is designed to be modular and extensible and can be used when a BERT or an RNN model needs to be explained. And if the developer wants to define a personalized model, the preprocessor and the predictor and the generator module should be provided by the developer. When deciding between these explainers for your use case, we recommend using the classical text explainer when using more classical machine learning models for NLP. And when you don't want to deal with the NLP pipeline, since this is quite simple to move components around within the explainer. However, when you need to understand neural networks, I recommend either the Unified Information Explainer, which allows you to understand information as it propagates through the layers, or the Introspective Rational Explainer, which provides strong guarantees on which phrases contribute towards your prediction. All right, now I'm going to switch over to the demo, and I'm going to show you these different explainers one by one. So the name of the explainer that we are going to look at first is the classical text explainer. And this is the technique that is used on classical machine learning models. And I keep telling you this information so you can memorize it. And so it covers the whole pipeline, including the text preprocessing, the encoding, the training, and hyperparameter tuning as well, all behind the scenes. And we are using bag of words encoder for preprocessing and logistic regression for training. And again, a quick reminder, as an input model, classical text explainer supports two model families, the scikit-learn and linear models and the tree-based models. Now, let's see how can we use this explainer. I'm using my local computer, by the way, and Jupyter notebooks installed on it. And if you want to get started with these things, I'm going to share with you my blog posts about this stuff, and you can try that out yourself. All right, as you can see in the first cell, I prepared the environment and defined the working directory. And then here, the data is imported, and thanks to pandas, now we can work with the data as a data frame. And the data frame looks something like this. And what I want to do is to predict for each of these sentences here. I want to predict what are their genre, which is defined here. For this, I'm going to make a data frame for my features and sentence. So the features are and the labels are defined like this. So we have the features and the labels there. And now I want to take a closer look at the genres. And I'm just going to write it out what kind of genres we have. We have telephone, government, travel, and all that. And we can also see here that the data is nicely balanced, which is really good because the model gets similar number of examples for each genre. So the predicted result won't be that skewed either. All right, so as I mentioned before, the classical text explainer takes care of the entire pipeline, and the label encoder of sklearn is going to be used for preprocessing. And it is time to prepare the dataset for training and testing. And we are going to use the splitting function of sklearn. And then we can see that we have 104,000 rows for training and 26,000 for testing. We can see the features and labels also prepared. And then the fit function of the explainer is available to train the machine that returns the classifier results and the best parameters as well. This is how the classifier looks like. And the pipeline configuration includes the preprocessor and the classifier as well, with the default logistic regression model. And the most important parameters are chosen from this list. These are the best parameters chosen for this scenario. And remember, the specification built from these parameters works well on the data set and model that are defined for this specific situation. And it maybe won't perform on the same way with the different configuration. And you can also choose different models, and that should be defined in a configuration file. So training happens with the fit function, and after training, we are ready to score our model. With the use of the test dataset, the labels now can be predicted, and as a result, the accuracy, the precision, the recall, and the F-score can be reviewed. And here we can see that the results are pretty good. It's 84% sure about the prediction it makes. What we want to do is to test the model and explain the decision it takes. Now, we pull in the possible labels into the explainers, and then we explain the prediction about the specific string that is defined here. For the first step, I want to choose data from the data set. We trained the model a bit, and I'm going to show you which one is this. This is going to be the 0 index, so this one is going to be the sentence. And we see that the government is the genre for this one. So I expect when I'm testing my model that when I pass this sentence to classify it, it should return this genre. Let's see how our model works. So I go back to my code where we can test it, right? The explain local function here requires of the feature as the parameter that has to be categorized. So, the model will figure out the label for this feature. And this function returns some really useful information. For example, we can see all the possible labels that are available for us that we can choose from. And to see which words are important, the explainer would rank them. And the information can be gathered with this code here. And the result would show the important words here. And it is the more important words are in the beginning of the list. And then the values can also be written out, and the corresponding values for the words are shown here in the same order. So you can see one is the most important and the negative ones are the not important at all. Okay. And finally, it's also able to return the predicted label. And just for your easier overview, I just return here what was the text, what was the original label, and the predicted label, which is pretty good. But like from these numbers and just like looking at this, it's not really giving you any better information. You could say that, okay, we have the product is the most important one, the skimming is also important, and so on and so on. But there is an interactive widget that shows whether the specific word has an effect on the prediction or not with this dashboard here. And what we can do here is to show some important words. And I'm going to make this a bit smaller so it makes more sense. So, yes. So to generate and view this dashboard, you basically have to run these 2 lines of code here. And when the slider at the top, with the slider here, you can define how many features you want to show on the dashboard. And on the right side, that you can also see the label that is given to the provided document. And under this, you can also choose to see all the features or only the positive ones or only the negative ones. And by hovering over the bars in the graph, you can also see the importance values that we just seen before. So note that it is showing now the result for a predicted label here. You can see that for this label, these words are having a big effect on the decision of the model. And Microsoft right now is working a lot to make it available to get an explanation of other labels as well, which should be defined in this function at some point as an extra parameter here, which class you want to explain your model for. And now I want to play a game with you guys. And that's why I like this Teams kind of situation, because we can actually do some game here. So what I'm going to do now is that I wrote a sentence here. We had a great time at your party yesterday. Thank you a lot for the invitation. And I'm going to give it to my explainer. And I would like you to guess which label will it define for this sentence. You're welcome to shout it out. So which label do you think should be parsed for this sentence? No one? So should I go ahead and tell you?
Fiction?
Come again?
Fiction?
Did you say fiction?
Yeah.
Okay. So let's see what my machine thinks. My machine thinks it's a telephone. I also show you which words made it do this decision. It says that it's the great, thank, lot are the most important words for this decision. And the negative ones, the yesterday, invitation, party, was the ones that would make the decision towards another label. All right, because, maybe you are not thinking like the machine does. Obviously, my machine is trained on some data set that you haven't seen before. So this is why my machine makes a decision based on that information that it got. So that's why it is interesting to explain why did it make that decision and how did it make it. So with the use of the classical text explainer, it is quite smooth and quick to put together a training pipeline, and the evaluation of the model is more straightforward and understandable. And users get a really good overview of how the model uses the data that is provided, which allows them to improve the pipeline easier. Now, let me go ahead and show you how the unified explainer is working. I'm going to make it a bit bigger so you see better. Right. So this can be used when a unified and intelligible explanation is needed about the transformer, the pooler, and the classification layers of the particular deep neural language processing model. And text preprocessing is handled by the by the explainer, and then the tokenizing is handled by the BERT tokenizer, obviously. So the developer must provide unified information explainer a trained or a fine-tuned BERT model with samples of trained data. And because the support of RNN and the LSTM is also going to be implemented in the near future, but it's not available right now. So the notebook environment and the working directory is defined with this code snippet, and then some variables are defined here that will be used for training, such as the quick run, because it is possible to decrease the runtime by setting this to true. But note that doing so will affect the performance of the model. Additionally, the batch size can be set based on the configuration of the device where the training would run. And you can use this is available function of PyTorch to check if your environment is fitting for a bigger or a smaller batch size. So for this demo, I'm going to use the same data set. And here's a fragment of the data set as well. So showing the labels and the features, so the genre and the sentence. And it is also visible that we have a very nicely divided data set, and it's very balanced and everything. So the data now is going to be splitted for the training. And we use again this train test split function. And sorry, and the label encoder of sklearn is going to be used for text preprocessing. And since the quick run is true, it is possible to pass only a fragment of the entire data set, which was defined in the beginning of the notebook. But again, this will maybe reduce the performance of the model too. So then after the transformation, the number of training and test results, the features together with the labels are returned. So this is all the data that we are training with now. Cool. So before just passing the data to the model for training, it has to be prepared by tokenizing. And for this test, the BERT tokenizer can be used for both the training and the testing data. And after this processing step, the model will receive the data as a list of tokens. Then in these two lines, some extra preprocessing is done, such as just showing you, such as specifying the beginning and the end of the sentence, the token length, how the token length should be, and you can read more about the BERT tokenizer at this link, but I'm also going to provide you these notebooks later. Right. The next step now is to load the pre-trained BERT model with the use of a sequence classifier there, specifying the number of labels and the language as well. And here we do training with the use of the tokenized training data, the defined batch size, and the number of epochs. And remember, these variables were also defined in the beginning of the notebook, and you can change it anytime to get better results. So this step also involves fine-tuning the BERT transformer and learning the linear classification layer on top of that. And the classifier is now ready to score the dataset. So the accuracy here returns 63%. That is not that cool. But again, it's just because we are training on a very small amount of data. So that's why. And we can see the results for each and every labels as well. Cool. It is very important to understand what happens behind the scenes, how the model decides based on the different words, which label to assign to a sentence. And the following code, for example, would return the configuration details for each of the layers of the classification model. I'm just going to just scroll down a bit so you can see all the encoder, then the layer here, first layer, then the second layer. And you can see all the information about the layers as well. All the details. How did it work? What did it happen? How many features has been passed? How did it behave? Which is pretty cool, right? And to get an explanation of the model, the Unified Information Explainer needs to be initialized by passing the model, the dataset, and the CUDA device as well, and the target BERT layer, so because we are able to explain whatever layer we want. We can define this one, you can just put in the free number here, or whatever layer you want. So we are going to explain the 14th layer. Then, yes, a prediction step is performed on a chosen test data. I hope you have seen this code before, like something like this at least. And then the explainer is called on it. And the result returned shows the test input, like what was the word, the sentence, sorry. The actual label, this is the actual label and the predicted label. So it seems like it works fine, even though it is just 36% sure about it, but it seems to be okay still. All right, so with the use of the Unified Information Explainers, users get a good overview of how the model uses the data that is provided, which allows them to improve the pipeline easier. And it works very well with deep models and helps you to understand what happens on each and every layers. And here again, similarly, you can get out which words are more important and which are not. And similarly, you can build a dashboard here as well. And now I would like to show you another scenario with an explainer that is also working well with deep neural networks models. And the data holds opinions about different movies. But first, we have to configure, obviously, our run. So we define that CUDA is false, quick run is true, and all that. So for the data that we are going to analyze is about different opinions about movies, concerts, and so on. And we want to see what is the sentiment of these comments. And to generate an outstanding text fragment of important features for training a classification model, Introspective Rational Explainer uses a generator predictor framework. And this tool predicts the labels and organizes the results, whether the words are useful or should not be used for training. And the anti-rationals, or the ones that should not be used for training, are filtered out before the training. And the API is designed to be modular and extensible and can be used when a BERT or an RNN model needs to be explained. And if the developer wants to define a personalized model, the preprocessor, the predictor, and the generator modules should be provided by the developer. So, yes, again, when you set the quick run to true, remember that it's going to affect the performance of the model. And in this case, it also skips over steps. It skips over the embedding and most of the evaluation as well. The Introspective Rational Explainer supports either RNN or BERT or the combination of these. And this configuration defines that BERT is not going to be used. I'm going to use RNN only. Then the next step is to import the dataset for training using a predefined function that extracts the data and builds a pandas data frame, which is now ready to use. And some data sets are defined here and there for the features, training features and testing features. And then the model configuration is updated also with the labels and the number of the labels. So all the labels and the number of the labels also added. And now if I review the data set, you can see that there are some sentences and the labels, whether it is a positive or a negative comment. Okay. It is now visible that the data is sort of balanced. So we have both positive and negative pretty nicely. And the GLOVE, or the global vectors for word representations preprocessor, this is going to be used as a preprocessor. This will tokenize and embed the data. And the labels then get appended to the output of the tokenizer. I hope you still can follow me. Right. So right now our training data looks like this. After specifying the tokens, it is getting a mask and it gets some number of how many labels that are added. Alrighty. Then, okay, I'm going to scroll this through. So, yes, as the next step, the explainer is initialized here and the preprocessor is set up. And the model configuration, this line, in the model configuration is also passed to the explainer and the training can start. The aim of the classifier is to identify the sentiment of each sentences. And as a result of this code, the details of the models can be reviewed as well down here. And it also returns the configuration details again for each layers of the classification model. This is pretty cool. All right, after the prediction, we can return the accuracy for a model. Again, not a very nice accuracy. And it is important, again, to understand what happens behind the scenes. So how the model decides, based on the different words, which label to assign to the sentence. And it is clear now that how the model is built up, how the layers are configured. Let's take a look at the data. What are the important features that has an effect on the prediction? So I passed a sentence, a beautiful and haunting examination of the stories we tell ourselves to make sense of the mundane horrors of the world. This is the sentence I'm going to pass to my explainer. And I'm again returning the words and the values. And you can see I have a few words here. This is not all the words from our sentence. It's because it is excluding the not important ones, right? That makes sense, I hope. And this is the important values added to these specific words. Now let's take a look at the dashboard as well. So this dashboard by default returns only the positive features. Do you remember when I mentioned how it works, right? The generator filters out the negative features during the training. And when you use the quick run, the model sometimes does not train very well, which returns odd results. So for real world scenarios, you might want to use a real run with both the deep NLP models explainer, so the unified and the introspect as well. But here we can see all the important words that are used here, also the importance values. And we don't have negative features since it is filtered out. So we only have the positive features and the label given is positive. So it seems to be a positive comment. All right, so now I switch back to my slides. So again, when you want to decide between the different explainer for your NLP model, you can use the classical text explainer when using the classical machine learning models for NLP, and then you can also understand neural network, like deep neural networks, if you use the unified information explainer or the introspective rational explainer. And as I said earlier in this session, this is an open source toolkit and we really welcome contributions. And please check out the repo at the link like this, this link here. And take a look at other additional resources on both the Microsoft Responsible AI Resource Center and Interpret ML. And if you have any questions, you are welcome to reach out to me. And I also wanted to show you quickly where can you reach out to me. So first of all, you can go to codewithdeep.azurewebsites.net, which is my blog where I write about all these explainers, and I write down how can you put it together yourself. And for each explainer, you can find details as well, how to set up the environment, and then how to write your own code and how to use this for your own models. You're welcome to reach out to me on Twitter with the Eve Pardi handler, and you can find me on Facebook as well. My Facebook page is at Code with Eve. And I hope you found this session interesting, and feel free to reach out, contribute, and ask questions. Thank you a lot.
Thank you, ma'am. That was a great session. I really enjoyed everything what you have taught so far. All right, we'll just open it out for Q&A right now. So anyone who want to ask your questions, you can directly unmute yourself and talk to the speaker.
Hello.
Hi.
Hi. So you talked about NLP, right? And basically NLP and LS teams, right? So this is a little out of context, but can this be used in image processing, like for CNNs and all? Maybe when they have, contextual information between slices. Suppose in medical imaging, we take an example. So
That's a really good question. Yeah.
okay, like just a few more words. So in CT scans, we have slices, right? And they have contextual information between the slices. So can this be used there? Just a assumption from my side.
Yeah. So CNN based models are not yet totally covered by this, and interpret ML is mostly, and interpret text specifically that I talked about was about text processing, but interpret ML itself, I think they are going to have some extra model coverage. I will take a look at that, whether it is coming soon or whether it is on the roadmap already, because I haven't heard if it is on the roadmap yet. So yeah, I wrote it down. Okay, I will ask it and make sure that it's going to happen.
This works. Yeah, thank you so much.
I thank you.
Yeah, Sunidhi, you want to ask something?
Yeah, I wanted to ask like there were neutral, positive, and negative expressions, right? So there were like Boolean values, right? 0, 1, and there were 4, 3 other numbers also. Like I didn't understand what that meant. Like 4,
Okay.
5, and
Yeah, I think I know which one you talk about. So at the
yeah, the
time
code one. Yeah.
when I was putting together this big tokenized data, right?
Yes.
So it is because first of all, you are concatenating tokenized data. The tokenized data would get some training data, some testing data, and connecting labels and all kind of preprocessed information. This is basically the number of features in it. So it's not really how it's like how many labels are passed. So in this token, the first token includes 17 features with 17 labels with it, for example. Does it
Okay,
make
like
sense?
in the below you have 2, 3, 4. Okay, those are just the numbers, right?
Yes, these are just this really doesn't have really a meaning. It's like this is like a token calculated with
Okay.
the use of this processor. And this is for this specific label, we put together a token which is masked with the labels, and then we know also that we have 17 features in it.
Yeah, I got it. Thank you.
You're welcome. Thank you for the question.
Anyone else? feel free to ask any doubts regarding AI here. It's okay if it is not related to this particular session.
Okay, like I'm Sunidhi again. I'm working under liver cancer reduction using whole slide images. We are using unit architecture for doing it. Am I audible? Okay.
Yes.
Yeah, so that's what. Do you have some suggestions which algorithm to go for?
I'm specifically not working with images, but
Okay.
I know people who does,
Mm.
and I could ask around to make
Okay.
sure, because I don't want to say something stupid, you know. I rather ask someone who is actually working with images.
Yeah, okay. Thank you.
I thank you.
So this is Yash. Can you
Hi.
hear me?
Yes.
Yeah. So we are the data set here was sentences. So
Mhm.
can this work with like a bigger data set?